The difference of electrical charges between the two sides of the membrane exists in all cells. This is because the membrane of a cell acts as an interface for the cell to exchange nutrients with the environment, and as a window for it to communicate with the other cells. Therefore, the membrane of a cell becomes a capacitor because ions and molecules with electrical charges cannot cross the membrane as they do in solutions, and this gives rise to the difference between electrical potentials across the cell membrane. The resting cell has effective mechanisms that interact with the actual cellular environment. Gradients of ions are formed by an enzyme in the membrane called sodium-potassium pump. This enzyme actively controls the gradient of sodium and potassium ions by enabling the outward flow of 3 sodium ions from the cell in exchange for 2 potassium ions into the cell, using the energy of 1 ATP per exchange. Ions inside and outside the cell are driven to cross the membrane by their gradient and by the net electrical force across the membrane. The balance between the force from gradient and the electrical force can be described using the Nernst equation, which reveals the relationship between the membrane potential and the concentrations of ions on both sides of the membrane. Proteins called ion channels, on the other hand, selectively allow specific ions to cross the membrane under certain conditions. In resting neurons, some active potassium channels give the membrane high permeability to potassium ions, and the overall exchange results in an equilibrium state where the inside of the neuron has more negative charges compared to the outside.